In this video, we are going to master how to construct a grouped frequency distribution. By the end of this chapter, you will be able to create a correct grouped frequency distribution table from a given raw data set. And you will be able to clearly explain key concepts like class limits, class boundaries, class markers, class widths, frequency, relative frequency, and much more. So stay with me and let's build this together. Before we dive into the step, let me remind you what a grouped frequency distribution table actually is. That is nothing but a grouped frequency distribution is a systematic way of organizing, presenting data into classes and frequencies. As we construct the grouped frequency distribution table, we will encounter several key important terms that define how data is grouped and interpreted. These include class limits, unit of measurement, class boundaries, class widths, class markers, frequencies, cumulative frequencies, less than cumulative frequency, more than cumulative frequency, relative cumulative frequency, and relative frequencies. To explain each term in grouped frequency distribution, this frequency table will be used in what follows. So what is class limits? Class limits are nothing but the smallest and largest values in each class. For example, from these three class intervals, each class interval has its own lower class limit and upper class limit. For example, while the lower class limit of the first class is 10, the upper class limit of that class is 19. The lower class limit of the second class is 20, the upper class limit of that class is 29. These class limits help organize raw data into intervals for frequency analysis. Unit of measurement, the gap between two consecutive classes. What's the gap between the two class intervals? The first class starts from 10 and ends with 19, whereas the second class begins from 20 and ending 29. So what's the difference between this one, 20 and 19, which is the gap of the two class intervals or the two classes, is nothing but 20 minus 19. This is nothing but the unit of measurement, which is used to calculate class boundaries and ensure continuity. Class boundaries eliminate gaps between adjacent classes. What was the gap with the class intervals is we have seen under the unit of measurement. Now that one is divided into 2. It becomes 0.5. So we subtract 0.5 from the lower class limit of a class and we add 0.5 to the upper class limit of that class to obtain the upper class boundary and to obtain the lower class boundary in such a way that we obtain these class boundaries. For example, for class 1, the class boundaries are given by 1. By subtracting 0.5 from 10, we obtain 9.5, and we added 0.5 to 90. Then we obtain 19.5. Therefore, this is nothing but the class interval in terms of class boundaries. This was 20 as a class limit, but we subtracted 0.5 from it, we obtain 19.5. Therefore, instead of class limit, now this one is the lower class boundary of that class. As we can see, there is no gap between 19.5 and 19.5. Continuity is there. So, class boundaries eliminate the gap which is created by the class limits. Boundaries are used to plot histograms and ogives. What is class width? Class width is nothing but the span of a class interval or the distance of a class interval. This class interval can be obtained by subtracting the lower class boundary from its upper class boundary of a class, or the discrepancy between two consecutive class limits or two consecutive upper class limits, right? Or class width is nothing but the discrepancy between two consecutive class marks. This all gives us 10 by 3 methods. This is the method of class boundaries, this is consecutive class limits, this is class markers. So this class width ensures uniformity across intervals and affects the shape of the graph. What is class mark? It is nothing but the central value of a class interval, the average of the two limits of a class, which is the sum of this class divided by 2 is nothing but class mark. 10 plus 19 divided by 2 is 14.5, which is the midpoint of that class, where this 10 is the lower class limit of class 1, whereas 19 is the upper class limit of that class. We sum these two and divided by 2 gives us this one. The same is true for the rest classes. So these class markers are used to plot frequency polygons and calculate averages for a given grouped frequency distribution. What are frequencies in a grouped frequency distribution? This is nothing but the number of observations in each class. In our context, for the first class, we have 2, meaning that we have 2 students whose score is from 10 to 19. we have 6 students whose score is 20 to 29. The total number of students are 12. These frequencies show how data is distributed across intervals. Less than cumulative frequency is running total of frequencies up to a given class. For example, the cumulative frequency of class 1 is 2. The cumulative frequency of class 2 is 2 plus 6, 8. The cumulative frequency, or less than cumulative frequency, 8 plus 4, 12. Meaning that how many students whose score is 19 and below? There are 2 students. How many students do we have whose score is 29 and below? 6 plus 2. And how many students whose score is 39 and below? This is nothing but all the students. This is nothing but what the reference is the upper class limit of a class and below. So these particular figures are useful for estimating percentiles and plotting ogives, the more than cumulative frequency, which is running total from a class downward. Class 1 has a cumulative frequency 12, which is more than cumulative frequency 12, meaning that how many students whose score is 10 and more, or how many students do we have whose score is 10 or above. Now we shall have 12 students. When we proceed to the second class, how many students do we have whose score is 20 and above? Then we subtract those 2 students whose score is below 20. 12 minus 2 is 10. So we have 10 students whose score is 20 and above. The same is true. This one, the third class, is nothing but we begin from the 30 and above. So number of students whose score 30 and above is 4. This is nothing but more than cumulative frequency. What's the relative frequency? Relative frequency is proportion of each class relative to total. What's the share of each class in proportion? In such a way that we obtain these decimals that sums to 1. So the relative frequency for the first class is 2 divided by 12. This denominator is the same, which is the total of the students, whereas these 2, 6, 4 are the respective frequencies of each classes. So these are nothing but the relative frequencies. Relative frequencies allow comparison across data sets of different sizes. Similarly, we can calculate also relative cumulative frequency. Cumulative frequency as a proportion of total. We have computed less than and more than cumulative frequencies. So we can calculate the relative cumulative frequencies for each respective. For example, relative cumulative frequency for the less than cumulative frequency can be computed by this formula. The cumulative frequency of each class divided by the total is nothing but, for example, was the less than cumulative frequency of the first class is 2 divided by 12, this one. The less than cumulative frequency of the second class is 8, right? And we divide by 12, this much. This relative cumulative frequency helps visualize cumulative trends and supports percentile estimations. Now, let us see one example of constructing grouped frequency distribution from the scratch. In doing so, we have raw data set on students' exam score on an exam out of 50. This record was for 20 students. Following the constructing steps, we will have complete grouped frequency distribution at the end of this lesson. So, what the objective is to make, organize, and present in a tabular form through constructing the grouped frequency distribution for this raw data set. In doing so, we follow some steps. So what the first step is, we determine the range of the raw data set. Range by definition is the discrepancy between the maximum value and the minimum value of the raw data set. So what the maximum value of our data set is nothing but 39, the minimum is 6. So the discrepancy is nothing but 39 minus 6, which is 33. This is nothing but the range. Range helps us decide how wide each class should be. What the second step is, deciding number of classes. To how many classes our data set is going to be organized is determined by this Stripes rule. This is nothing but 1 plus 3.322 times log n, in our case 20 to the base 10. This is computed to 5.32, but In this, usually we round up 6 classes. So still we determined the range and determined the number of classes. What is left now is class width. Class width has also its formula. Class width is determined by the ratio of range and number of classes, which is our range is 33 divided by our number of classes is 6, which is 5.5, and rounded to 6. Right? Was the first step of constructing group frequency distribution table is constructing class limiters. Most of the time we start from the minimum value of the raw data set. What was the minimum value of our data set is 6. So we can start from that value or less. But for this example, let us start from 6. Right? The lower class limit of first class will be 6 now. To this 6, we add another 6, then we will obtain the lower class limit of the second class, right? To this 12, we add 6, where 6 is now class width, right? 18. We add 6 to this 18, 24. The lower class limit of the fourth class is now 24. We add 6 to this one, 24, we obtain 30. Then we add 6 to the 30, 36. So this element is now of lower class limiters, right? To the upper class limit, we obtain by calculating the lower class limit plus class width minus 1. Our lower class limit is 6. We add the class width, which is 12. Then we subtract 1, which is 11. Then the upper class limit of the first class is 11. Then from this, it is easy to obtain this series. We add 6 for every subsequent upper class limits, right? For example, to obtain the upper class limit of the second class, we add 6 to the upper class limit of the first class, which is 11 plus 6, 17. This is now the upper class limit of the second class. The same is true. This one can be obtained. Therefore, this table is now the number of classes corresponding to the class limiters. 6 up to 11 is now one possible class. 12 to 17 is the second possible class. 18 to 23 is the third possible class, interval or class, right? So this number of classes was determined by the Strags formula above, and the 6, which is the class width, was determined by the class width formula. So most of the time, lower limits begin from the minimum value and increase by class width. This is as a rule of thumb. Now we count how many students whose score is within this class interval, within this one, within this one, this one. Right. We have 2 students whose score is from 6 to 11. Right. We don't have other data points or scores whose score is with this one. Only we have 2 scores, 6 and 11. This 14 is out of the range, that class, out of that class. Now expressed ascendingly, it is easy to identify which scores to which class intervals. So let me turn me back. Right. So we have 2 students whose score is within this class interval, and 2 students within this interval, and we will have 7 students whose score is from 18 to 23. This is nothing but the class intervals versus the frequencies. This is the basic group frequency distribution. This one ups and downs is to obtain this table. Now this one is the basic, but optionally we can add another terms to this table, such as relative frequency percentage, less than cumulative, more than cumulative frequencies, class markers, and much more. Now let us construct this group frequency distribution in terms of class boundaries, right? Here we have seen, for example, let us consider 2 consecutive classes. For example, the first class from 6 to 11, the second one from 12 to 17. Here we can notice that there is a gap between 12 and 11, right? The gap is nothing but 12 minus 11 is 1. This is the unit of measurement. So was the objective of constructing class boundaries is nothing but to eliminate that gap, right? In doing so, we subtract 0.5 from each lower class limits of each class, and we add 0.5 to each upper class limits of each classes, in such a way that we come up with this element, right? We subtract 0.5 from 6 and we obtain 5.5. We add 0.5 to this 11, this one, right? And the class mark is computed by 6 plus 11 divided by 2, which is 8.5. 12 plus 17 divided by 2, 14.5. Now, for example, the class width can be obtained from this discrepancy. 14.5 minus 8.5 is 6. Or from 20.5 minus 14.5 is 6. We can obtain the class width from these consecutive discrepancies of midpoints. Or from this one, from 11.5 minus 5.5 is 6. Or 17 minus 11 is 6. 12 minus 6 is 6. Right? So in such a way that the class widths can be computed to be the same. But the other important term that we can add to our basic grouped frequency distribution is cumulative frequencies. For example, less than cumulative frequency for our class, which is the third class, 18 to 23, is nothing but 11. How can we compute? Recall that computing less than cumulative frequency starts from the upper class limit of the first class. How many students, for example, how many students whose score is 11 and less, or 11 and below? We have 2 students, right? And how many students do we have whose score is 17 and below? 2 plus 2 is 4. How many students whose score is 23 and below? This is nothing but 11. This one. More than cumulative frequency is nothing but the lower class limit of the class and above, right? How many students whose score is 6 and above? 20. All of the students have scores 6 and above. These are 20. How many students whose score is 12 and above? This is nothing but we subtract those 2 from this 20 to obtain this one, right? Therefore, this grouped frequency distribution adds this frequency and more than cumulative frequency elements. What other important thing is relative frequencies. Relative frequencies is nothing but expressing the respective frequencies of respective classes in proportion. For example, the relative frequency of the third class, which is from 18 to 23, is 7 divided by 20, which is this one. When we multiply this relative frequency by 100, we come up with relative percentages, right? This becomes now 35%. This is 55%. But the final frequency distribution table, consisting of all possible terms, looks like this, right? This is a grouped frequency distribution table for those 20 students exam score raw data set, which consists class limits, class boundary element. This is class mark. This is frequency, less than cumulative frequency, more than cumulative frequency, relative frequency, relative cumulative frequencies. These are the legend for these abbreviations, right? So this one is a well constructed grouped frequency distribution for our raw data set. Thank you.